Thank you very much for attending my workshop today. Before we get going, all the content that we are going through in this workshop is available. If you go to nlpfromscratch.com/TMLS, that will redirect you to a GitHub repo where all the content is, so I'm just going to do that now. You point your browser to nlpfromscratch.com/TMLS. Hello. That should redirect you to the GitHub repo for this workshop. And there is my face. That's unfortunate. So if you scroll all the way down to the bottom, you will see a badge here that says Open in Colab. So if you click on that button, that should open the notebook we will be going through in Colab. And then once you're in Colab, if you go up here to File and then Save a Copy in Drive, that will create a copy of the notebook that you will have forevermore and that you can also run independently from what I am running, okay? So once again, the URL is nlpfromscratch.com/TMLS, or you can go to github.com/nlpfromscratch/workshops/fine-tuning-TMLS-24. And the content, including the slides we're going to go through today, is there. Thanks again for coming. I guess I should say who I am. So I'm Myles Harrison. I am an AI consultant and trainer. I have just started my new business, independent freelance and training business, NLP from Scratch. Previously, I spent many years in the consulting world in data science and AI, places like Accenture and PwC. And now I'm doing my own thing with NLP from Scratch. Okay? The other thing I will say, hello, welcome. The other thing I will say is that if you are a machine learning engineer and you have written production code in PyTorch or Keras or something, this workshop is not for you. Please get up, leave the room, and make fun of me, okay? This is an introductory workshop for people who have a little bit of knowledge of Python, a little bit of knowledge of LLMs, and are not highly technical, okay? All right, no one left. That's great. Yeah, and so if you want to share or take a photo of anything that you see and share it on social media, I would appreciate it. And all the handles for NLP from Scratch on various platforms, GitHub, YouTube, Discord, meetup.com, are all just /NLP from Scratch, one word. Okay, hello. I'm going to put this up for just 1 second. Those of you that just joined, again, if you go to nlpfromscratch.com/TMLS, the content is there. And you need to open the Colab notebook. All right? So while we're all getting started, what I'm going to do is go back to my copy of the notebook if my keyboard will respond. And if you've never used Colab before, this is just a notebook that is backed by a cloud instance of compute on Google's cloud. So just two things we need to do before we get going. If you go up to runtime here, I'm going to make this bigger so people can actually read it. Now look how big my face is going to be. Okay, so if you go up here to runtime and then down here to change runtime type, just check that the hardware acceleration there is on T4 GPU. It should be for everybody. Google actually provides free underpowered GPUs through Colab at no cost. And some of the stuff we're going to do in this introductory workshop is a little bit old and busted, but also you can run it on free Colab and probably your crappy laptop, which is probably better than my crappy laptop. Okay, so just make sure that's on GPU. And the next thing I'm going to do is go up here and click Connect, and that will spin up some cloud infrastructure to back this notebook. And it's just a little check mark here, and you can see that we have a machine with 12.7 gigabytes of RAM and 15 gigabytes of GPU RAM. That is better than my machine. I think I'll just leave now. That's embarrassing. Okay, so I will introduce what we're doing in the slides. That is my face again. Why did I choose to do that? That's a poor choice. There's some information here about the setup for the code we're going to be going through. If you haven't used Colab before, anytime there is a code cell like this one, you can either hit the little play button, just like on a VCR, if anyone knows what that is, or you can highlight the cell, as I like to do, and then hit Control. I should have done that about 15 minutes ago. Yeah, that's better. Or you can hit Control and Enter, and that will run the cell. And in this very first cell, we are downloading some data sets that are just text data that we are going to use from the nlpfromscratch.com GitHub. And then this other cell here, we are just installing. Okay, somebody did leave. Thank you. And here we are just installing the Python packages we are going to use in this notebook, and that's going to take some time. So now I'm going to go back to the slides. Okay? Did I lose anyone? All right. So while people are working on that, let's talk about what we're going to talk about today. So I've already done the introduction. Hello, nice to meet you. I'm Myles. Let's talk after. And today we're going to talk about generative text models, which people probably know what those are if you're here at TMLS. We're going to talk about fine-tuning LLMs, and we're going to see an example of tuning a very old and busted but very important LLM in code. And I will do my best to make this as simple as possible, but not simpler, so that it is actually very clear what is going on in the code. Okay? All right, so just a disclaimer quickly. I don't work for Hugging Face. I don't really know anyone at Hugging Face. They're not paying me to get up here and use their product. I'm not an official representative of Hugging Face or any other organization except myself and NLP from Scratch. So if any of this code is wrong or busted or old, which it probably is, I take full responsibility. Come back later and tell me. But Hugging Face is becoming very quickly a standard library and framework for working with large language models, and that's why I'm giving this workshop in it. Okay? I work for myself. I'm an independent consultant. All right. Okay. In my half a decade of running the global data science team at a tech boot camp and teaching there, as well as time teaching at a traditional educational institution in AI, I have developed a little bit of a manifesto about how people learn. I believe that knowledge is only valuable if it's useful. We're not here to get our PhDs and become research engineers, so this is going to be hands-on stuff. And also, I have some other beliefs about how learning is not a linear process. You don't need to go all the way from zero to the end of a 2-year, master's program in order. That's not how people learn in the workplace, and that's not how people learn. Also, teaching and learning are complementary. I don't know everything. I'm up here sharing the knowledge that I have and what I put together, but I am sure I could learn something from every single person in this room. Okay? I'm going to pick up the pace here because there is a lot of content to crank through, and I'm going to see how much we can actually get through in this hour and a half and change. Okay, so very quickly, let's talk about generative text models, which hopefully are new to no one, unless you've been living under a very warm rock for the last couple of years or so. So what the heck is an LLM? It's the name of my webinar, but also in case you didn't know, a large language model, or LLM, is a type of machine learning model. I think people have kind of given them this mythic magical status, but they are literally just a type of neural network that's very big. The other thing that's worth noting about them is that they have a different architecture. The vast majority of LLMs today are based on some variant of the transformer architecture, which was introduced by Google Brain in 2017. And the L in large language models obviously stands for large. Both the size of the data set, we're talking about double-digit percentages of the web, and also the size of the model in terms of the number of parameters, right? We're talking about models with hundreds of millions, billions, or now even trillions of parameters in the case of like GPT-4, which has 1.76 trillion parameters and is a mixture of experts model, okay? So, different transformers. The transformer actually has two parts to its architecture. There is the encoder type transformer and the decoder type transformer, and then full encoder decoder as the original transformer was, all right? Credit for this visual from Abby Morgan from Common ML. It's a very good visual. So encoder only models, maybe people are familiar with BERT. They take in input data and they produce what we call an embedding, which is a numerical representation of text. Decoder only models is probably what most people know, things like GPT and Mistral and what else? I don't know, Phi and things like that. The vast majority of these are for text generation only, and that's what we're going to work with today. And then full encoder decoder are less common now, but there are some models like BART and things like that that are a bit older, and they're better at sort of these more traditional NLP tasks. Okay? So today, oh wait, I thought there was supposed to, anyway, we're focusing on the stuff in the middle. Today we're talking about decoder-only models. All right? So in order to talk about that, we need to talk about different language modeling tasks. At the top, we have mass language modeling, or MLM, where the task is to predict the blurred out token, right? This is one of the language tasks that the BERT model from Google was trained on. This is how it was trained. The vast majority of generative text is what is called causal language modeling, or CLM, where you are trying to predict the next token, and then you use that token to make your next prediction, and you use that token to make the next prediction, and so forth. So this is why people talk about decoder models as being auto-regressive, because they are making predictions, and then they are making predictions based on their predictions. It's also why when you give a generative text model a lot of freedom and it predicts out very far, the performance starts to get worse and worse, right? This is also the part of the presentation where I check to see how old people are, because auto-regressive models is like, yo dog, I heard you like predictions, so we put predictions on your predictions so you can predict while you predict. All right, so we're going to be talking about causal language modeling. Absolutely 0% of the room got that reference. Foundation models that maybe people are familiar with from Google, the encoder only, the sort of foundation model of foundation models was BERT, which was a bidirectional stacked encoder. So many people use this. You put text data in, you get an embedding out that is a numerical representation based on the data you train it on. Decoder only, obviously GPT from OpenAI, which we're going to work with today. Everyone, including your grandmother, even if she's dead, knows what GPT is, right? And then not as many encoder decoder only, but the T5 model from Google is sort of the foundation of foundations of encoder decoder. And this was sort of a Swiss Army knife model that did lots and lots of different things. Okay? But this is all old news. This is the original OG foundation models. We're talking 2018, 2020, or earlier. Okay, so, oh, that's where the circling was. Right, so today we're going to talk about decoder-only models because we're doing generative text, and we are going to work with GPT, not through an API. I saw you giving me that look. Okay, so what are the use cases? I don't care about any of this LLM hype unless it's actually useful, right? There's plenty of snake oil across the street if you want to buy some. So use cases for generative text. In my opinion, the most and best one is actually to just write other code. Obviously, lots and lots of productivity uplift and lowering the bar in terms of the barrier to entry for software engineering from tools like GitHub Copilot and other code models like CodeStroll. So this is really the most, I think, important one. Writing assistants, people have been using these tools now to create a never-ending stream of AI-generated content and written emails that you should call people on. Thank you for another email written by ChatGPT. I appreciate it. And the one most people don't think about is actually the entertainment value. I was very surprised to learn that of the top 50 Gen AI companies used by consumers, rated by Anderson Horowitz, that character AI is actually number 2. And if you don't know character AI, one of the original authors of the Attention is All You Need paper, which introduced the transformer architecture, went there. And they basically have different chatbots that are different characters, like you can chat with Elon Musk or your favorite anime character or what have you. Okay? So these are the use cases. Hopefully the stuff we do is useful. Okay, if you don't know what GPT is, this slide is just to sort of show the history. We're going to be working with GPT-2 today. Boo. It's still got 1.5 billion parameters. It's still not very good, but that's what you get when you train your model on data from Reddit. I don't know what they were expecting, but the point of this slide is to show that over the span of not even 5 years, we've seen a 10,000-fold increase in the size of these models. All right. So really crazy how fast things are accelerating. And I don't actually know how many parameters GPT-4o has, but I assume it's also in the trillions. Okay, which brings us to Hugging Face. How many people in this room have heard of Hugging Face before this workshop? Everybody? That's good. How many people in this room have used Hugging Face before this workshop? Oh, okay. How many people in this room have done fine-tuning with Hugging Face before this workshop? Okay. All right. I hope you still learned something new. And if we have questions after, you can chat, because I don't want to waste people's time. But Hugging Face is interesting because they're kind of this weird animal where they're both a platform and a company and also a software, right? Hugging Face makes the transformers library. They make the datasets library, the diffusers library, but they're also a company with a lot of valuation behind them, billions of dollars from lots of big names. And they're also a platform, huggingface.co, where they store snapshots of LLMs and datasets and things like that. Okay? Today we are primarily going to work with the transformers library, which unsurprisingly is for working with transformers. Not the little robots, but the large language models. Okay, so all these things together is what made Hugging Face pretty brilliant, really. They took deep learning platforms like TensorFlow, PyTorch, and JAX. They wrote some higher level Python API code on top of that to make it easy to use. They store the model snapshots in Git LFS. They store the data sets in PyArrow, and then they have inference endpoints that are hosted and run in Docker containers. Put it all together, and what do you get? Hugging Face, the platform, Hugging Face, the software. Okay, and if you already have a Hugging Face account, that's great. But if you don't, you can go to huggingface.co and then sign up with an email. It is free. It costs nothing. You don't need to do that to complete this workshop, though. That's just if you want to push your fine-tuned model to the hub. Where did the rest of my slides go? Oh, I need to go all the way. Oh, my goodness. Sorry, that was an errant keystroke. Okay, we were here. So I think now, with that errant keystroke, we can go back to the notebook and start talking about actually working with generative text models. So again, I'm running this on Google Colab free. So I'm trying to use very low-end hardware here. And I will tell you that we're going to fine-tune GPT-2 XL by the end of this notebook on Google Colab free. Okay? But for now, we're going to work with GPT-2. I know it's not the new hotness. It's fairly old and busted. But if you are learning, it is a good place to start. And also, it's still incredibly popular. You can see GPT-2 was downloaded almost 7 million times last month from the Hugging Face Hub. So it still remains very popular as a base model for learning to work with LLMs. All right? Okay, so how does text generation actually work? Now I need to go back to my slides for a bit. People think that text generation is some magical different machine learning problem, and they say stuff like, oh, LLMs are different than traditional machine learning because they're probabilistic and they give you a different output every time and things like that. And I'm here to tell you that that is all bullshit. Because really a deep learning model, an LLM, is just a deep learning model. It makes predictions like any other type of neural network. And the only thing that is different is that you are predicting a class where the different classes are the different tokens or parts of language. So it's not some magical, completely different thing. You literally just have a multi-class classification problem with very, very high cardinality, that is to say a very, very large number of possible output classes, every unique token across the entire corpus that the data set that the model was trained on, and that's the task, all right? So it's multi-class classification. I put the input, the rain in Spain falls mainly in the plain, into the model, and then it gives me a sequence of output probabilities based on the data it was trained on of what it thinks is the most likely occurring next token. And here, the most likely occurring next token is plain. So we take the most probable next token, which is plain, and then the next token we predict would be the word plain. Does that make sense? It will make sense more when we go through the code here. Okay? And this is what that, or no, let's go back to the notebook first. Okay? So the easiest way, this is not large enough for people to read, is it? Should I make this bigger? I'm going to keep making this larger until someone waves their hand and tells me it is too large. Too large? Too large now? Is that large enough? Yeah, okay. If you want to generate text in Hugging Face, if you can write 3 to 4 lines of code, you can do that. That's how difficult it is to use an LLM. 4 lines of code, can we handle that? Okay, so here we're importing Torch, which is the deep learning library. Then from the transformers library, we're importing the pipeline abstraction. Pipeline is very, very high level. And then we are just checking here if GPU is available with this line of code. And then here, we're making a pipeline. And the type of pipeline is for text generation. We're specifying to use the GPT-2 model. And then we are telling it to use the GPU that is available on Colab. All right? What does this string actually mean? That means it's going to go to exactly huggingface.co/GPT-2. So that is the model it is going to use, okay? And then after that, here now is where we actually do the text generation. I'm going to make a new variable called outputs. I'm going to put in my quote-unquote prompt, I love applesauce, and then I'll tell it to return a maximum of 40 tokens and to return 3 different possible outputs from the model. Okay? So this is just setting up the model here, and then this is actually doing the text generation, and then I'm printing it. So I'm now going to run this cell of code by hitting play. And when I do that, Hugging Face will do a whole bunch of stuff without asking me for permission. And it will take a long time because I am presenting, just like how if you wash your car, it will rain. Okay? So you can see a whole bunch of stuff. Whoa, what is happening? It just pulled down half a gig without asking me, all right? And that is the actual weights for GPT-2 from the Hugging Face hub. So those were just sent over the wire. It's a crazy time we live in. Why am I talking so much? I'm going to run out of time. Myles, you're talking to yourself. You're in front of a lot of people. I know. Okay, this is getting weird. All right, so it's crazy the time we live in where the amount of information that flies over the wire, like you can run this Hugging Face code and it will pull down like 6, 7 gigabytes over the wire, and then you just throw it away. And you're like, oh, okay, I don't need that model anymore. Anyway, I wish I had better internet at home. So it pulled down the model, and then it loaded the model into memory, and then you can see here, it ran the model and generated our text. We put in the input string, I love applesauce, and it gave us back the string, I love applesauce. I could never get over how it tasted like, something, something. Okay? So that's it. 4 lines of code to generate text with an LLM. Lots and lots of complicated AI things happening that are abstracted away. I should also point out that I'm really cheating because this wasn't even GPT-2. This was a smaller version of GPT-2 from the GPT-2 family. If you pull down the full GPT-2, which is called GPT-2 XL, this is GPT-2, right? So this is only half a gig. That's weak. That's not even a large language model. Half a gig? Come on, Myles. GPT-2 XL, which is a full 1.5 billion parameter model, you can see is downloaded much less often and weighs in at a hefty 6.75 gigabytes. And that's what we'll fine tune later on Colab free. I hope. No, you all know I'm going to run out of time before we get there. Okay, so the pipeline is a very, very high level abstraction. If you take a look at the pipeline, it actually has a tokenizer inside of it. And then it also has a model inside of it. So for those of you that are not machine learning engineers, or no, wait, let me do this first. You can check the number of parameters the model has. And as I said, we're using a smaller version of GPT-2. So this GPT-2 just has a paltry 124 million parameters. That's weak. Boring, Myles. Okay, I'll go. I'm sorry. I'm not going to go. I'll stay. So it's actually a super high-level abstraction, and now I need to explain to people what a tokenizer is in case they haven't used a tokenizer before. So this is sort of the process for how getting a machine learning model that only understands numbers, i.e. like a deep learning model, to generate text. We put the text into what is called a tokenizer. The tokenizer comes up with, which for all intents and purposes is just an index for each part of the language. So you can see it returns the numbers 1, 15, 22. So the number 1 refers to the word the. The number 15 refers to the word rain, and so forth. So it's really just like a lookup for the different words, but it's actually like a multi-class classification problem with a very, very high cardinality, right? And then because we're doing transformer stuff, the tokenizer itself is also a model, and we get what is called an attention mask, which is just a Boolean flag that tells the model where it should pay attention to the different words, and that's as much as I'm going to say about that. Okay? But the tokenizer itself is also a model. All right? Just to break up the language is a separate model that was trained. Then we put that information into the generative model, and then it will give us output token IDs, which again are just class labels, as the result. And that will be the words that come next. And then we put that back into the tokenizer to sort of do like a reverse lookup, and then we get the language that comes next. Okay? So that's a fairly high-level explanation, basically, of how this text generation process works. Yes?
So here for the output token IDs, each label refers to the arrays that represent the right?
Each label refers to what?
To the array, to the token IDs that we generated into this step.
Yeah.
For example, number 22 in the output token IDs, okay?
Yeah, I just picked
Refer to the first array.
I just picked these token IDs randomly.
Yeah, I know the number.
Yeah,
I
but
want to know the logic behind it.
you're putting in the token IDs and the attention mask are your input data, and then the target for the model is the output data, the output labels. So it's a multi-class classification problem.
I want to know the difference between the token IDs and attention mask and output token.
Yeah. Well, the stuff on the left is the input.
Yes.
The stuff on the right is the predictions from the model, the output token IDs. And we definitely do not have time to talk about how the attention mask is generated. So I'm just going to be a university professor and just wave my hands over that. And
For the output token class ID, should not be one next token or one year master?
yeah, I think, sorry, what? This is probably not right then. I need to fix my slides because what you're getting is actually the whole string plus the next token, right? Because you'll notice if we go back to our notebook, and my keyboard does not work again for some bizarre reason, we put in the rain in I love applesauce, and then what we got back was I love applesauce, I could never get over, right? So, okay. So, using a pipeline is fine for sort of like walking around, but the sort of best practice way to do this is to use a tokenizer and a generative and a model separately, okay? So then we go through these steps, take the input, tokenize it, generate the sort of transformed input, put it into the model, generate the token outputs, and then move it back to text. That's sort of like the best practice way to do it, all right? These tokenizers and models this is different than traditional NLP. You have different tokenizers that are trained to work with specific types of models. And that's what Hugging Face has abstracted away in their classes. So for us, we're going to use GPT-2. So there's a model type GPT-2. And then the GPT-2 model has an associated GPT-2 tokenizer, right? If you use the wrong tokenizer with the wrong type of model, it's not going to work. Just like how when I went to Canadian Tire and I bought the wrong type of windshield wiper. Why am I telling this story now? Okay, let's move along. So this is the way it looked with a pipeline. And now that we've imported everything, it's literally like one line of code, GPT-2 pipeline on the input, and you get the output. okay? Boring. Yes, that's fine. Yes, yes, we don't need to do that. Okay, so this is the way it should look. From transformers, import auto tokenizer, and we're doing causal LM, i.e. generative text. So there's an auto model for causal LM. We instantiate the tokenizer by saying auto tokenizer from pre-trained, and then the name of the model, here GPT-2. Then we create a model by saying auto model for causal LM from pre-trained, GPT-2, and then I put this annoying pad token thing here to stop a warning from occurring, and then we have our input string, okay? So that's just setting everything up, all right? And now we have a separate tokenizer and a separate model, all right? And now when we want to transform the text into the model inputs for the generative model, i.e. the stuff that is happening on the left side of this slide, we just pass our text into the tokenizer, and then here this is just telling it to put the output into GPU, not CPU, okay? And when we run that and print the result, this is literally the input that goes into GPT-2. It is a big tensor, which is just the token labels, all right? Those are just class labels. And then the attention mask, which is telling it whether or not to pay attention to each token. And in this case, I don't have to answer any more questions because the attention mask is all ones. Ha, okay. So now we pass that input into the model. And if you are familiar with this double star sequence, which I hate and I think is a stupid syntax, it just takes each part of this dictionary and then passes that as a parameter to the function call. So here we're just taking our model, that's GPT-2, and then we're just passing in that transformed class labels and attention mask. And that is it, literally. Now if I print this, oh, sorry, it's not it. So that has now done part 2, i.e. the part where in the middle where it goes through the model. That's the part that we've done now, all right? How are the people that have like worked with Hugging Face before not like really bored now? Like I thought like 4 people would get up and walk out. That's what I would have done. But I'm also very rude. Okay. It's not rude, though. It's a conference. People come in and out of. Okay. And now we pass the output that we got into the tokenizer, and we call decode, and this does the reverse operation and converts the class labels back into tokens. Okay? And then if we print the result, oh no. Did I not run a cell? I think I have to run this cell. Run the cell, Myles. You're talking to yourself again, Myles. Oh, it's because I didn't import Markdown. See, this is what happens when you don't run the notebook all the way from the top all the way to the bottom. And now you're talking to yourself again in front of a big group of people. And no one is laughing at this joke, and I'm just going to keep doing it. There, someone snickered. Okay. So now we need to import this, clickety-click. Okay. There we go. So we put the rain in Spain falls mainly in the plain into GPT-2, and we got back the rain in Spain falls mainly in the plain of the Canary Islands, but also in the, and then we stopped because that's as much as we asked it for. Okay? And people are like, hey, it's supposed to say, how can I help you today? Sir, did you know the odds of successfully navigating an asteroid field are 1 in 100 billion? And you're supposed to be like, write me an email. We'll get to that in a bit, okay? That's what underpins these chat models. But this model, this is the base, like GPT-2, where you just generate text, and they refer to that as a base model.
Why did we stop this, but it is also in there? Is it because it reached the limit of tokens, or is it because it's doing step by step?
I told it when I instantiated the model up here. Or no, I didn't. Okay, I guess there's a default sort of distance that it predicts out, and you can set that.
It's the token one.
Yes. Thank you for clarifying. The thing that I didn't clarify, whereas I'm the one giving this presentation. Okay, so that's everything we did, right? 3 real steps. Take the input, convert it into tokens and an attention mask, take the input tokens and attention mask, put it into the model, get output token IDs, and then take the output token IDs, put them into the tokenizer and decode them, and get back English language. Yeah.
In previous cells, right, when you ran to get two different outputs, when you ran, it got a set of output from the LLM. When I ran, I got different set, which is expected, right? But this time, I got the same set of tokens as output.
Yeah.
Did
So
we do something for reproducibility or?
yeah, we'll talk about those things in next. And that is also why I say that when people say things like that LLMs are probabilistic and give you a different output every time, it's bullshit, because there's actually an additional layer on top of there. But LLMs, when their weights are frozen, are completely deterministic. You can run this notebook 100 billion times, and you'll always get this same output from GPT-2, which is the rain in Spain falls mainly in the plain of the Canary Islands. Yep. Okay, which brings us, segues nicely into the next section. So you're on the right track. You segued nicely into the next section, which for some reason is not the title of my slide. This workshop was going to be so professional when I rehearsed it, and now I'm up here talking, and this is what happens. Okay, so let's talk about text decoding strategies, all right? So I don't know if you've noticed, but when you talk to human beings, if they say exactly the same response to everything you say to them, it's a bad experience. There's variability in how we get answers and things like that, and so this is a desirable quantity that researchers, with what they make look complicated with math, but is actually super simple, artificially inject variation into LLMs to make them seem more kind of human-like and usable in the text they generate. Okay, so again, for those of you in the back, you sir, I like your shirt. It is not AGI, fight me. And then also, it's 100% deterministic, okay? All right, we're artificially injecting this randomness. Okay, so that's basically what all that text says. You can read it on your own time. So let's talk about different text decoding strategies. The default decoding strategy, called greedy search, is not a search at all. All you do is take the most likely next token by the probability score and use that. So always pick the most likely token, token by token, as you predict. Okay? That's not even a search strategy. You can call it greedy search, but that's exactly what you would do with a normal neural network when you're just doing any class prediction. It's just converting soft predictions into hard predictions. Okay? We have one that's 60% probable, class 1. We have 40% probable, class 0. The hard prediction is class 1. All right? Beam search is different. Okay? Here, you keep track of the most probable tokens at each step, and then you don't choose the most probable token at each step. You predict, you take the beam of the flashlight that has the most probable collective probability over the whole width of the beam. And 50% of you are just like, what the hell did that sentence mean? And I will show you. In general, beam search works pretty well with certain types of tasks, but in other cases it doesn't work so well. And with a lot of these things in LLMs, it starts to get a bit murky, and it's sort of a try it and see type of thing. Do I go to the next slide? Okay, yes, I do. So on the top, we have greedy search. The input is, the rain in Spain falls mainly in the. As I said, the word plain was 60% probable. It's the most probable, so we pick it. And then we use plain to make the prediction of the next token. And then which is 55%, which is greater than 45%. So the output would be the rain in Spain falls mainly in the plain which. That's greedy search. Okay, that's the default behavior. Beam search is different. You have to calculate now all these different paths, so it's more computationally intensive. But you can see that even though plain is the most likely token at 0.6, if we go step by step, when you go, if you're going to take a picture, like put it on LinkedIn. The slides are on GitHub, right? I'll send it out after. Okay, I'm sorry, I'm not trying to be rude. I'm just saying all the content is in the deck, which is in PDF on the GitHub. Whereas here, you can see that grasses is 0.9 probable, meadows is 0.4, so the collective probability is 0.9 times 0.4, which is 0.36. Whereas plain is 0.6, and which is 0.55, which is only 0.33, which is less. So we would take the second beam, and if we use beam search, we would say the rain in Spain falls mainly in the meadow grasses. Okay? Which is the right answer? There isn't a right answer. It's generative text. Which metric are you optimizing for? The whole probability over all the tokens, or the next token, right? As the beam gets wider, it gets more and more computationally expensive because you have to do the autoregressive prediction for all the different possible combinations across all the beams. Greedy search is easy. Just go token by token, next token, and it's just linear, right? So that's another disadvantage of beam search, is that it is computationally expensive. Yes?
So is width the same as the number of output tokens you want, or is it going to be different?
Is width the same as a number?
If I wanted like 5 output tokens, five tokens to be output,
Yeah.
width would also be 5 or 4, right?
I see what you're saying. I think in practice you would rarely do that because then your beam would be really big and you probably would have a shorter beam and then it's a sliding window, right?
So which one is used out there? Does it depend on?
It really depends on the situation. You can look up in, like even like OpenAI's documentation, like what the default values for these types of things are. I believe that this is actually less commonly used now, and that the stuff we talk about next, like temperature and like top P, top K, is more frequently used with greedy, as far as I know. Yes?
So the computational inference is going to be like C to the power of n, where n is the width of the beam and C is the number of options. How many?
If you say so, yeah.
Kind of athletic. How many options do you get for like meta? Like we always get like only 2 options, or do you get multiple potential options?
Okay, so again, why is my keyboard doing this? So again, it's a multi-class classification problem where the number of possible classes are the number of tokens across in the entire vocabulary of the training data. That's why it's expensive, okay? It's a very, very, very thin tail, and I don't know, but I assume that there's some sort of computational assumptions they make where it's like if the probability is 0, 1, 10 to the negative 6, we don't care. So they probably make some shortcuts there. But yeah, technically speaking, the number of possible output classes would be the total number of distinct tokens in the vocabulary of the training data for the model, base model. Okay, cool. So let's look at beam search, or actually let's look at greedy search. Why didn't I do this earlier? There, that's better. All right, cool. Why didn't I do that earlier? Oh, you know what? Why don't I do this? Man, I should do this for a living or something. Okay, so there's some mathematical stuff here talking about the probability, but basically, that's just a really fancy mathematical way of saying that we're taking the highest probability and then turning the soft predictions into hard class label predictions. Okay? So how does that look in Hugging Face? We've already seen this. Put it all together. Import the tokenizer and model. Create the tokenizer, create the model, give it an input string, and then create the outputs, and then generate the outputs. So for greedy search, it's the default behavior. This is all the code we saw earlier, just put together into one block. There's no parameters you need to change or anything. And as you can see, oh wait, we had to do this. As you can see, why did I put this into separate blocks? Okay, so as you can see, again, greedy search is deterministic. We get the same output. The rain in Spain falls mainly in the plain of the Canary Islands, but also in the something. Okay, so that's greedy search. And just to prove my point for you, again, if you run greedy search, it's not sentient, it's not probabilistic. I can run a different generation. I will get exactly the same output for a different variable that has the same input. Okay? And that's why in-context learning is a misnomer and is also bullshit. Okay, so beam search, as I was talking about, there's the visual, and we talked about this. Here what you do is you set the number of beams. How many beams do you want to search across? And to the gentleman's question there, it's going to be the top 10 most probable, right, for each step, okay? This early stopping equals true also helps with the computation because it says, look, if there's a beam and I know there's already a beam that has a higher probability, I don't need to calculate that beam because I know we're not going to pick it, right? So you only calculate the beams that you know that you need. And that's it, okay? So that's the only thing you need to change. And if we do that, this cell should take a little bit longer to run. And now we get a different most probable output. The rain in Spain falls mainly in the plain to the south of the city of Barcelona, okay? Because it picked the outputs that collectively were more probable, not the most probable token by token. Okay, which brings us to sampling strategies. This is where people artificially introduce this randomness to make the outputs of the LLMs more creative, so it's more like talking to a person, okay? So I feel very strongly about this, as you can tell, because I'm burning even more time by saying it. When does this thing end? 2:30? Again, LLMs are just a neural network. They're not some super special type of model that is like different than other machine learning, that is probabilistic in its outputs, and will give you, it's not. They just add this additional layer on there to make it that way, okay? So next time someone starts giving you that like sort of nonsense, just tell them to check themselves before they wreck themselves. Okay, so the different sampling strategies we have, the most important one is temperature, and then there's also another sampling strategies called top P and top K, which are basically the same way of doing the same thing, but just keeping track of it differently, okay? So let's talk about temperature. Many OpenAI users here? Anyone? Oh, okay, I thought it'd be like everybody. Yeah, you can set temperature when you make API calls to GPT as well, right? So the temperature is just a way to inject variability into your output. So the higher the temperature, the more sort of diverse and random your outputs are going to be, okay? Whereas the lower the temperature, the more sort of deterministic they're going to be, all right? So if you set the temperature to 0, temperature of 0 is the same as greedy search. You'll always get the same output every single time. Whereas setting the temperature really high, you're giving the model a lot of freedom, and then you get, shall we say, very creative outputs, i.e. gibberish. Okay, so there's a balance to be struck, and I think in OpenAI's API, the default value for temperature is something like 0.7, and their scale goes from 0 to 1. Okay? So what does temperature actually do if you're a little more technical? When we have a neural network and we have a multi-class classification problem, which LLMs are doing, as I said, just a very, very high cardinality one, you use a softmax function to take the outputs of the neural network and then convert those into probability scores that are between 0 and 1 and add up to 1, okay? So what they've done with temperature is you artificially introduce a parameter t, and then you divide each output by t before you put it into the softmax. So what that means is that as t goes to infinity, you're just going to get 0 for each output, and the softmax of 0 is going to give you an equal probability for all tokens, right? So if your temperature is high, you are literally just randomly picking a token next, okay? Whereas if the t is 0, yeah, you can't actually set t to 0 because then you would get an indeterminate. But when the t is very, very small, you basically just get the figure at the top, which is greedy search. Pick the most likely token next. Okay? But short story long, high temperature, more variability, low temperature, more deterministic. Okay, so let's look at that in code. And there's some math there if you want to read that about how that works. Okay, so all we need to do to use temperature in Hugging Face is in our call to model.generate, we set a parameter temperature, And this parameter, I believe, can be any value. It's not like OpenAI. It doesn't go between 0 and 1. I think you can set this to be like, 1,000,000. The other thing that you do need to do is set this do sample equals to true. The default behavior for Hugging Face is to not use sampling strategies, i.e. to use greedy search. So if you want to use temperature and top P, top K, you do have to set the do sample variable to true. Okay? And that is it. Everything else is the same. We still tokenize the data the same. We still generate the outputs the same. All the magic is happening in the model.generate. Okay? So here I'm setting temperature to be a very, very low value, and that means the outputs are going to be very, very predictable and be the same. And you can see that here because I made 3 generations, and I got the same string that we saw before with greedy search. The rain in Spain falls mainly in the plain of the Canary Islands, but also in the, right? So that's low temperature, deterministic, always the same. Yeah. Yes?
Sorry, clarification question. What does number of recurrent sequences mean? Model.generate requirements?
That is the number of outputs that it returns. So it just runs the model 3 times. And here, because the temperature is low, we just got the same output each time. Whereas now, thank you for queuing up the next part, whereas now, if we set the temperature, oh, it does go to 1. Okay. So here, let's set the temperature to 1. This is the default behavior in Hugging Face. So now we're going to get some randomness injected. And you can see we generated 3 different outputs, and they're different. The rain in Spain falls mainly in the plain in Sonia in the middle of August. The rain in Spain falls mainly in the plain, and then it drops slowly and sometimes rapidly during these. The rain in Spain falls mainly in the plain in the southeast. In the west, the rainfall is. Right? So now we get different outputs each time because of that randomness. And now, if I was really crazy, which I am, because you people have been listening to me for this long and heard me talk, you know that I am, if we set the temperature to be very high, here to 110 to the 8, now we get very, quote unquote, creative outputs because the likelihood of picking each token is essentially random. It's equally likely to pick any token. And this is still more coherent than me, even though it's randomly picking tokens. The rain in Spain falls mainly in the plain countryside between Sotendur, where it forms. The rain in Spain falls mainly in the plain below, in Greece, a bit further north. And the rain in Spain falls mainly in the plain south, as far as the north central. I think it's still fairly coherent because you still have an attention mask. So it's not complete gibberish, but maybe people have seen outputs come out of like GPT where you crank the temperature way up, and it's just like complete nonsense. Actually, we can just spin the wheel again. Can I set this to be higher? Let's set this to be higher. No, that's not very good. Can we set this to be really high? There we go. The rain in Spain falls mainly in the plain. Soft here on September, December, and summer 2018. Anyway, you get the idea. Okay, top P and top K sampling are different strategies. They can be combined with temperature, where you only look at the most probable tokens. So here, we're not going to look at all the possible tokens that could come next. We're only going to limit our selection to the top 5 most likely. That's where we're going to redistribute the probabilities. And then for top P, you give it a total probability, like here it's like 80%. And you say, you know what, I only care about tokens that add up to being 80% most likely for the next token. Okay? So these sort of kind of like clamp your predictions, and they get rid of all the sort of long tail tokens that we don't give a crap about. Okay? And you can use these in combination. Not sure why you would, but you typically use top K and top P together with temperature to get some randomness, but also to get the tokens which come next, which are more likely, which hopefully are more coherent. Okay? Which is what the next slide is about. Am I in the right notebook? I hope so. Yes, I am. Okay, so to do that, yes?
Is it true that if we use the temperature with the top, defining top K and top P, our model gets confused?
Gets what?
Confused.
Models don't get confused. They don't think.
Yeah, I mean that, for example, because we set all these metrics, I mean that
Yes. That's what we're going to do. Yep.
Ask my question.
Let's talk after, okay? Yeah.
How do you know what values, what range of values make sense for temperature?
That's the good question. There is no right answer.
Yeah, I mean, because if we had a range for that, then I had an idea, okay, not go with zero, but not, but if I don't have any range to the infinity, you know,
Yeah.
maybe a million is large for me, but 10 to the power of 10 is large in your mind.
Yeah, welcome to large language models, right? If you were doing traditional machine learning, you would have an accuracy score, you do hyperparameter tuning, you do grid search, randomized grid CV, whatever. You'd say, this is the best hyperparameter value. What's the right answer? Our outputs is text. It's human evaluated. So there is no right answer, and people, like, I am not joking. If you find an answer, let me know, but people typically just play with these values, and the geniuses at OpenAI were like, 0.7 is a pretty good temperature value. Like, people are like literally like vibe checking the outputs. Okay, I'm definitely gonna run out of time, so I'm gonna just skip over some of these parts. So here you can just add a parameter to do top P and top K, and you can see you just add a parameter to the call to model.generate, and you still need to set the do sample equals true value, and now we get different outputs, okay? Yes?
Sorry, do they A/B test the temperature value? Is that how they find out that when people are just thumbs up?
That would be one approach, yes. Yeah, assuming you don't mind pissing off some of your users. Okay. I'm sorry, that was indelicate. So how do you pick a balance between temperature and sampling? There's no right answer, as I said. Thank you for your input, both of you. If your temperature and top P are both low, you consider a very narrow range of tokens, and then it's very predictable. That's basically greedy search. If your temperature is high and your top P is high, you've got gibberish, and then stuff in the middle is usually where you want to be. Okay? All right, so let's talk about fine-tuning LLMs, which apparently I'm going to do in half an hour. This does end at 2:30, right? Okay, so in case you're not familiar, the different types of things that you do for training LLMs is different than traditional machine learning. You have a phase called pre-training, which no one in this room is going to be able to do unless they are a millionaire. This is what the companies like your Metas and your OpenAIs and your Googles of the world that have access to a lot of infrastructure and millions of dollars are doing to train the base model, right? This is where you're doing the L in LLM, feeding it the entire internet to train the model. After you're done that, you also have a reinforcement learning piece where there's a reward model. And then the thing we're going to talk about today that anyone can do because the amount of compute that you need and the data sets you typically use are very small is called fine-tuning. And in case you have done traditional machine learning, it annoys me because everyone's like, oh, fine-tuning. It's really just transfer learning, people. We used to do it all the time in computer vision. It's called transfer learning. They just gave it a different name to make it sexier. Okay, so again, pre-training, you're taking all the data and training against a target objective to get what you would refer to as the base model. Right? So for BERT, they were doing masked token prediction, next sentence prediction, and then when they're done, they get the weights for BERT, the base model, and they freeze those forevermore, okay? If anyone in this room has done this, please come and talk to me, because I'm impressed. But if you don't have millions of dollars and access to crazy infrastructure, you're probably not doing this. Reinforcement learning from human feedback, or RLHF, is not what we're going to cover today, but this is really the secret sauce that OpenAI discovered of making LLMs sound human and sort of steering their outputs to be a certain way. That's why when you chat with ChatGPT, it always sort of gives you these like bulleted lists as answers because people have reviewed the answers it's given in the past and said, no, that's not how you talk. This is how you should talk. And then you train a separate reward model based on those ranked outputs and then combine it with the original model to get a composite that behaves the way you want. So I think it's interesting because you teach an LLM to speak the same way you teach a young child to speak. It says a whole bunch of random stuff, including the F word, and you say, no, that's not how you talk, and then eventually, hopefully, the kid will talk the way you want, okay? What we are going to do today is fine-tuning. Yeah.
Reinforcement learning happening at the top of the train model. So is it very computational maybe as well? I mean that even if you have a, let's assume that you're using an open source model, can you run reinforcement learning at the top of that in order to?
Yes, I believe so. I believe it sits somewhere in the middle. Hugging Face actually has a separate library for doing reinforcement learning. On top of that, most people probably are not, because reinforcement learning is even more technical than a lot of LLM stuff. But my understanding is that it sits somewhere in the middle. So you're probably not going to do it on my laptop properly, but it doesn't require, millions of A100s or whatever to do. But if you find out differently, let me know, please. Yeah, I'm not really an RLHF like hands-on expert. So fine-tuning though, we can do. Here you take an existing model, you give it a small data set that is new, and then you say, hey, this is like how you should be speaking, and then you just like adjust all the weights little by little until it is fit to kind of that new, smaller data set. Okay? This is not the technical term, I basically made this up. But there's two ways you can do this. You can do what is called full fine-tuning, which is where you literally update every weight in the model. This is very expensive, right? If you think about GPT-2 having 1.5 billion parameters, you're turning 1.5 billion knobs. It's very expensive computationally, all right? But you get good results. What most people do is called partial fine-tuning, or in the old days, we used to just call transfer learning, where you freeze a lot of the weights, and then you either add new layers or only update certain layers' weights, and you're only playing with part of the mixer board, okay? Lots of great questions about this I've had in the past. Some people that are a lot smarter than me, which is basically everyone, knows which parts of the transformer, like which attention heads to freeze and which attention heads to tune based on, what they want to get out of it. But finding out that sort of thing is also a lot of work. Okay, so we're not going to do this today, but I'm sorry. If there's time at the end, let's take questions. I really have burnt so much time, so if people want to talk after, I'm sorry. I'm just going to have to keep crushing ahead. Okay. This is an example we're not going to do, but a very common example is to take BERT, which is not a decoder model, an embedding model, and then just slap a classifier head on BERT, and then train those weights to be able to give it text and do a classification task. Okay, so that's a very, very simple, you can do this, I think, on your laptop easily. And this is a very common use case. Take BERT as the foundation of foundation models for an embedding and then just turn it into a classification model. Okay, and if you want to see an example of that, somebody here from this text attack package, they took BERT based on CAST, which is one of the most popular models on Hugging Face. They gave it the Yelp binary classification sentiment data set. They did a little fine tuning, and now there's BERT based on CAST Yelp polarity. And you now have a fine tune from BERT, which is an embedding model, which is now a classification model for sentiment. Okay, so it's taking all the knowledge that's in the weights of the embeddings in BERT and then using that to do classification, which again is just transfer learning. But now we call it fine tuning. Okay, so let's go hands-on finally with fine-tuning. And to do this, I thought, now I have to think about someone that has a certain way of speaking that is unique, right? Where we could fine-tune a model and get it to speak a certain way where it'd be like, yeah, that worked. And I'm like, who has a really unique way of speaking? And then I thought of my second favorite Jedi Master, Yoda, from Star Wars, who obviously has this way of speaking in short, sort of non-grammatical sentences. So let's see if we can fine-tune GPT-2 to be a Jedi Master. Sounds like fun. Okay, back to the code. Why are there so many slides now? That's weird. Okay. So again, we're just going to be fine-tuning the smaller GPT-2 medium to start. But doing so is not so bad. First, we need a data set. We already downloaded the Yoda data set, which I painstakingly put together myself. This is 214 some lines of dialogue from Yoda across all the different Star Wars movies, including those really bad ones. You know the ones I mean. So it's literally just free-form text, very small data set, 214 or something like that observations, okay? Sorry, it's not even that. It's 103 lines of dialogue.
It's worth coming just for those lines. Thank you.
It's like a big secret. Like, George Lucas is at home like, yeah, that was my best work. So from the datasets library, we import load dataset, and this is just loading the data into a Hugging Face specific data format that they use, okay? And now if you take a look at that dataset, you can see it's a dataset dict. This is just the format that Hugging Face uses for their framework, okay? So that's nothing too special. And now we go through the same process we went through before. We need a tokenizer, which is the GPT-2 tokenizer, and we need a model, which is GPT-2, and we instantiate those, okay? So these are the same steps we did before, where we would be using the model for prediction, right? But now we have the model, and instead of using it for prediction, we're going to give it new data and start playing with the weights and fine-tuning it to change its behavior. Oh, I don't think I have to say behavior in quotes. Okay, so here is an input for the model, the rain in Spain, and then we can generate output, and we did this before, and that's just to show that, you know, this is the same GPT-2 base that we're starting with, okay? Now we are going to give it some text data from our data set. The very republic is threatened if involved the Sith are, right? We need to actually set up a tokenizer function to tokenize our data set so that our data is in the format that the model expects. And we also get an attention mask. So after we do that, now you can see here, we have 5 different dictionaries where we have the raw text. We have the input token IDs, which came from the tokenizer. So these are padded out. You can see these are just the blank character. And then we also have the attention mask, which came from the tokenizer, okay? So we just tokenized our new data set using the tokenizer. Okay, so now to do the fine-tuning, there should probably be a slide for this, but I don't think there is. No, there is not. Okay, it's all code. Okay, so to do the fine-tuning and training in Hugging Face, you need to do a couple things. You need to have a trainer class. You need to have an evaluation metric to tell your trainer what you're evaluating against. And then you need to actually do the training. Oh, you need data. So we have data. Now we're going to set up the trainer class. So from transformers, import training arguments, which are the arguments for the trainer, and then trainer with a capital T is the class that does training. And here I'm just setting up the training arguments. So we're going to store our new fine-tuned model in the Yoda-GPT-2 directory. We're going to train it for 10 epochs. That means it's going to see the whole data set in its entirety 10 times. And then the evaluation strategy is going to be per epoch. And then there is an accuracy metric from the Hugging Face metrics package. Accuracy in this case being, does it predict the next token exactly each time? Okay, still can't believe that's how LLMs work, but apparently it is. Are we out of time yet? Almost. Okay. And now we have this utility function. I'm just going to breeze by this. You have to use this data collator, at least for this example. I think there are some examples now where you don't have to do the data collation. I was like, what the hell is this data collator? And really, it took me some figuring out, but all it really does is it takes your data that's in a format like this with the text, the input IDs, and the attention mask, and then it sort of just pivots it. So now you have one big set of data with an array of text, an array of tensors for the input IDs, and an array of attention masks. That's literally all it does. You'd think Hugging Face would write that in the documentation somewhere, but they have not. Okay, and then this is the trainer that we're setting up. So here we tell it the model name, GPT-2, we give it the training arguments, we give it the data set. Here I'm evaluating the data on the same data it's being fine-tuned on, which apparently no one cares about because overfitting is not a thing when you do LLMs, but please don't do that. And then we give it the data collator to transform the data. Okay, and now that is it. Now we are good to go, and fine-tuning the model is as difficult as calling trainer.train. Okay, so that was all we had to do. Data, trainer, data collator, and the metric. and then you're done. And now I call trainer.train, and now it is going to read in the Yoda data set. So for each epoch here, it is now adjusting the weights of the GPT-2 model based on that Yoda data set. Okay? And this is not taking very long at all because this is a very, very tiny data set and a very small model. When you're doing this type of fine-tuning on a large model, you obviously need a lot of good hardware. And when you're doing it on a larger data set, this would take hours, a very long time. Yeah, or wait, I said I wasn't going to take more questions. I have 15 minutes left. Let's talk after, okay? Maybe the next guy will be late. Okay, and now we did 10 epochs, we're done, all right? This is also not really very well documented, but if you're like me, you want to actually take a look at the training loss, and this is actually stored in the trainer state. And there's our training loss, and you can see it's going down and not ping-ponging or anything. So that's actually good. We only did 10 epochs of training, but there's no like weird overfitting or anything happening. And the model actually learned because the loss is going down, so that's good. I'm not a complete hack, I just talk that way. Okay? And then finally, we call trainer.saveModel, and that will dump the weights that are in memory to a file. And in this case, it's in that directory Yoda-GPT-2, and that's where it's dumping the weights. Okay? So now if I take a look in the Yoda-GPT-2 directory, you can see it's saved the model as a safe tensor snapshot. It's saved a bunch of other stuff. And we can see because it was based on GPT-2, it also takes up about half a gig, just like the original model. That's it. Fine-tuning before your eyes in a free Colab notebook. All right? And now we can use the model to make new predictions. So here, I'm going to be lazy and just use a pipeline. I'm going to give it input text that says, Luke, you must know that. And then I'm going to instantiate the text generation model, only now I'm going to load it from the local drive of the Colab notebook in the Yoda-GPT-2 directory. It's still a model of type GPT-2, so it still uses a GPT-2 tokenizer. And then this is the same as before. We just put the input into the model and generate the outputs. And now if I do that, we will get outputs from the fine-tuned GPT-2. And we get outputs like this. Luke, you must know that you are not. The Jedi must confront you. The Sith must destroy you. The dark side must be eliminated, and so forth. So that sounds like Yoda, right? So we have successfully fine-tuned GPT-2 with just a few 10 epochs of training, right? And that's it. Yeah, and I know somebody in the audience is saying, well, you could do that and get outputs like that with regular GPT-2, and I did that, and it usually thinks Luke is like Luke from the Bible, and you get, outputs like that. Okay, but here we can see, tokens that are in the fine-tuned data set being recovered, like words like Sith and Kenobi and stuff like that. All right? What is this? Yeah, also if you don't want to save the model, it is stored in the trainer object, so you can load it just in memory. Okay, I think I'm going to pass by this part because it's just generating more text from the model in memory. And at this point, I want to actually reload the model so that I don't run out of RAM, and we can go on. So now, in all of like 12 minutes or so, I'm going to talk about performance-efficient fine-tuning and how you would fine-tune a model like GPT-2 XL with 1.5 billion parameters that is 6.7 gigabytes on a free Colab, and the answer is by cheating. So model quantization, how many people here know what model quantization is? Hands? It's okay if you don't. Oh, that's great. Okay. So basically these models are so big that if you store every weight as a floating point, it's very, very expensive, both in terms of RAM and in terms of compute. And this is a shocking finding. Researchers have found that if you just round the weights and store them like as integers, it takes much less memory, right? And shockingly, the model performances are still pretty good. And so this is called quantization. There are schemes for doing different types of rounding. And then you can do things like take a quantized model that wouldn't run on your laptop and then you trade some, shall we say, precision and performance for performance, for how computationally expensive it is, okay? So this is one approach to make the problem of training large language models more tractable. There's a whole family of approaches called parameter efficient fine-tuning, or PEFT. And these are different methods that researchers have come up with for the problem of training very, very large language models on limited hardware, okay? The most popular approach, if you Google PEFT, is what is called LoRa, or low rank adaptation. And then QLoRa is quantized low rank adaptation. This is research from researchers at Microsoft, and they also extended it to make the alpaca model with QLoRa, okay? All right, so how does LoRa work? Basically, you cheat. Instead of updating all the billions of parameters in the LLM, you get a matrix that is smaller, and then you convert all those weights into like a smaller matrix by doing a matrix multiplication. You train those small matrix weights, and then you do the conversion back. So you're basically taking all the weights in this big, big space and then doing a matrix multiplication to reduce them into a very low dimensional representation with algebra, right? With matrix multiplication, train those weights, and then, you know, move it back, all right? So now let's do parameter efficient fine tuning with Yoda. Do or do not, Myles, there is no try. And now we're gonna do it with GPT-2 XL on Colab free. I am the only person that is excited about this. Okay. So here's a section on model quantization. You can actually load a quantized version of a model just by specifying this load in 4-bit, and that will quantize the model. So here now I'm going to load GPT-2 XL, which has 1.5 billion parameters. You can see Hugging Face is downloading all 6.4 gigabytes of GPT-2 XL. If I tried to load this model in full precision into the Colab notebook, it would crash the Colab notebook because I would run out of RAM. But if you load it in 4-bit precision, it takes a lot less memory, and so we can actually load the full model with all the weights being like rounded to 4 bits, okay? And if you go on Hugging Face, there's lots and lots of different versions of quantized models that people have made, and even the process of quantizing the models takes like a lot of compute, and you can see here that it's taking some time just to load the model. Yeah, anyone know any good jokes? Okay, so that's just the quantization piece. And so we're saving memory there, which should make the training easier. Are you done yet? Come on. Okay, there we go. And now you can see, again, I'm not lying. There's nothing up my sleeves except my arms. There's 1.5 billion parameters. And this is a GPT-2 model. And we now have these 4-bit layers instead of the full precision layers. Okay, I got 5 minutes. So we don't need to do that. And now we're going to use PEFT. We're going to use LoRa. So here we first prepare the model for quantized training by using that from PEFT. Then we set up our LoRa configuration. So here we're going to reduce it down to only 8 dimensions. And then if you want to check, now instead of training, you know, billions of parameters, there's only 0.2% of the parameters we're going to train. And now everything else is the same. We set up the data set. We set up the accuracy metric. This is all the same as the fine tuning that we did before. What is different now, the only thing that is different now is that we use our new model now here, which is the quantized model. And we have now turned that quantized model into using a LoRa because we added the LoRa to the model. Okay, so now it's not going to update all the weights. It's just going to update the weights in the LoRa. And now I can call trainer.train. And I can hope that this works. Why is it doing this? Okay, getting a lot of warnings here. All right, we're off to the races here. So you can see it is now passing all the data from the Yoda data set into training GPT-2 XL. But again, we're sort of like cheating with this parameter efficient fine tuning. It's a quantized version of GPT-2 XL, and we're not updating all 1.5 billion weights. We are updating the weights in the reduced LoRa space. And then when we have those weights in the like LoRa space, you do the multiplication back and you invert it to get the updates to all the weights in the model. All right? But this is like, I can do this in Colab free, like literally before your eyes, right? I'm also only gonna do one epoch because I got shown the 5-minute warning sign. Okay. So that is now done. And now, when we use the LoRa model and generate some outputs, we're now using the full model plus the LoRa to make predictions. And you can see we get things like, Luke, you must know that I am Luke Skywalker, I am the Jedi, and so on. So the fine tuning on the data set has worked. Okay, I think we don't have time for any more code, but when you're done, you take the weights from the LoRa and then you invert the multiplication to move the updates to all the weights in the base model. All right? I'm going to skip over that. All right, final thoughts in 4 minutes. When you're fine-tuning, be mindful of the data. This is a hilarious example. Somebody fine-tuned GPT 3.5 Turbo on their Slack history, and then they said to it, hey, write a 500-word blog post. And it said what he would say. Yeah, sure, I'll do it in the morning. Right? Okay, so final thoughts. Why is this not like chat models? Really, the chatbot style models is just a trick of the way they set up the input data. So you have sort of these special tokens for the assistant and the user, and you're the user, and then it makes predictions, and it just sort of hides everything else from you, and that's how these chat models work. They're still just doing next token prediction. They're actually predicting the whole conversation, and then ChatGPT just shows you the part that comes from the assistant. So it's actually really very clever. They just sort of manipulated the input data and then said, hey, we're not predicting a book, a novel, we're predicting a conversation, and I'll just show you my half of the conversation. Okay? So you have these different message roles, system, user, and assistant, and you can see that there are like special tokens for user and assistant and stuff like that. And there are these chat templates in Hugging Face that allow you to do that. Okay? And again, it's specific to the model. Different models have different tokenizers, and they have different special tokens, and there's no standardization across the industry for that, which just makes it a nightmare. Okay, someone asked about RLHF, way beyond the scope of what we're talking about today, but there is a library that Hugging Face has made called TRL, or Transformer Reinforcement Learning. So if you're interested in training reward models, check out TRL. And also, people are probably familiar with RAG. Fine-tuning is actually a step you do later, where you're sort of teaching the model how to speak. If you want to do things like prevent hallucination or ground your model in a knowledge base, fine-tuning is not really the way to go. You're typically combining fine-tuning with RAG, where you're having the model hit a data source, a ground truth that it knows. Okay, so I cannot believe that I got through everything. That is it. Thank you very much for your time and attention. I'm Myles Harrison. If you would like to know more, feel free to shoot me a message and check out NLP from scratch. Thank you very much. So I'm going to stand up here until the next guy shows up and kicks me out. There were, I think, other questions that people had. So, yeah.
So I have two questions. The first one was, is there a way for the Transformers library to show you which attention heads that you're dealing with?
when you are like fine tuning and things like that?
Yeah, like I think at that point you were talking about how there are some people who know how to freeze which attention has.
Yeah. Yeah, that's like more you're in machine learning engineering type territory and things. It's not too bad. You would need to know a little PyTorch, and then I think you just have to go into the model and say, trainable equals false or whatever. So it's definitely doable.
There are trainable parameters.
Pardon?
The attention heads are trainable parameters.
I mean, the attention head is a big block, right? But the different weights, like that's not a Hugging Face thing, that's a PyTorch thing. Yeah, but basically the short answer is that if you want to do any sort of gritty, granular stuff that with Hugging Face, you need to know both PyTorch and Hugging Face. I'm just sort of doing like walking around Hugging Face stuff. Yeah. Yes?
So my question was that in the prompt engineering guide, I read that the general recommendation is to output temperature or top P but not both. And you said that you use in the Colab, but you didn't use both of them together. Okay, so you just said top K or top P or temperature, not both of them together.
I did in the example I skipped over. The prompt engineering guide is also just written by another guy that has an online course in AI. The right answer is typically yes, you use both. And the right answer for what should those values be is there's not a right answer because there's not sort of quantitative like hard metrics for text generation. But people have done sort of playing around with these sorts of parameters and found values that are reasonable. So even as I said, when you use OpenAI, they have default values for top K and top P. And if you use just like the vanilla OpenAI text generation, the outputs you get are quite reasonable because they've found these values. And those values also differ model by model, right? The good temperature and top P, top K for GPT may be different than the one for Llama or something like that. Yeah, so it's a process of trial and error, really. Yeah.
Is there any suggested amount or ratio of fine training data compared to the model size, like 1%, 10%?
That's a great question. I haven't seen baselines on that. Any benchmarks for that or sort of guidelines? Generally speaking, though the data sets for fine tuning are quite small. So like here you can see I used a data set of like 100 observations and got results. In my experience, you don't need a lot of data. Like you're typically talking maybe thousands of observations. There's no need to fine tune, as far as I know, with like millions of observations or anything. But the short answer is it's a weird world we live in now because the short answer is you can fine tune with very, very small data sets. And also, in the world of LLMs, no one really seems to care about overfitting, because the outputs are text. So I undoubtedly overfit the hell out of GPT onto that Yoda data set, but that's fine because I want it to speak like Yoda and give outputs that are very similar to the data set. Yeah. Yeah.
Just very briefly earlier, you very briefly mentioned that in-context learning was bullshit. Could you just elaborate on that?
Yeah, fight me. Yeah. So the CTO of Cohere tried to convince me that this is not the case, but I still disagree with him. If you do greedy search, the outputs are the same every time. Learning in machine learning means updating model parameters based on data. That's my definition of machine learning. When you do in-context learning, literally all it is different input giving different outputs. Nothing is being learned. The model weights are not being updated. It's literally just a different input gives you a different output. Shocking, right? But for some bizarre reason now, because of hype and funding and stuff, I don't know, researchers do dumb things like change the meaning of the word. They give it a label in their paper and they say, oh, it's in context learning. And it's a complete misnomer. So that's my take. Other people disagree with me. But yeah, they can fight me. Yeah.
What's your favorite LLM model for fine-tuning?
My favorite LLM model for fine-tuning? I mean, GPT-2 is easy, as we just saw. You probably are not going to get too far without already using a quantized model. So if you want to do something like Llama, you probably want to use a quantized one. I like the Phi models from Microsoft because they're very small, small language models, right? But with the chat models, when you're fine-tuning a chat model, you have to do more legwork to get the data into the format that you need to fine-tune a chat model, right? But yeah, lots of people hate on the Phi models, but I really like them. They're some of my favorite. I mean, obviously Llama is like a standard, but I like Phi. Okay, I think I have officially gone over time. If folks have more questions, I'm happy to chat later or shoot me a message either on LinkedIn or through the Hova app or what have you. Thank you once again for your time and attention.